Before we start, I want to thank our sponsor, Kyndryl. With a unique blend of AI-powered consulting built on unmatched service capability, Kyndryl helps leaders harness the power of technology for smarter decisions, faster innovation, and a lasting competitive edge. You can find Kyndryl at KYNDRYL, Kyndryl.com. In the digital world, code is the essential primary building block, the equivalent of the cell or DNA in the biological sphere, and almost as mysterious. Code can create entire worlds, real and virtual. It allows us to connect instantly to people and places around the globe, and it performs tasks that were once only possible in science fiction. It is a superpower, and not just in a technical sense. It is also a gateway to ideas. As vividly illustrated by today's guest, code is the ultimate connector, providing new insight and meaning into how everything from language and mythology to biblical text, even our patterns of thought, connect with the history and nature of computing. Today's book is his attempt to reinvigorate the human in the world of computing, from understanding how our machines can help us to think better, to seeing the similarities between the realm of language and text and the world of code and software. But computing also extends its tendrils into simulating entire societies, the nature of life itself, and the question of whether all of reality is just a computer program. It is a pleasure to welcome back, for the finale of our trilogy, the author of The Magic of Code: How Digital Language Created and Connects Our World and Shapes Our Future. Samuel Arbesman, welcome back to the show.
Thank you so much. Yeah, good to be doing this again.
It's great to have you, man, and thank you. Sam has just landed only a few hours ago at 5 a.m. and he still made our call happen, so I appreciate it, Sam.
My pleasure. No, I think I'll be lucid enough.
Well, if you're in a computer program, it doesn't matter. But this is a brilliant book. For those who have ever heard of the idea of the simulation hypothesis, if we're living in a simulation, etc., this book is the building blocks of how we got there. And that's towards the part 3 of the book, towards the end, where Sam talks about artificial life. But let's share your entire thesis behind this book, because for me, it was such a privilege to see how you'd built everything to get to here. And still, the common thread is the importance of humility and curiosity as we progress in technology.
No, I love that. Yeah, I definitely feel that that is definitely one of the themes that kind of goes through all of my books. But yeah, for this one, the way I think about it is, if you look around at the current conversation around technology and computing, it feels a little bit broken. Like, we're often like adversarial or worried about technologies. We're concerned about certain things around AI or about social media or phones and kids. And there's all these concerns. And those concerns are all valid. But when I remember my own experience with computers growing up, it wasn't just worry. It was also full of a huge amount of like wonder and delight. And not only that, it didn't just feel like computation was just this branch of engineering. It was really this humanistic liberal art that connected to language and philosophy and biology and art and how we think and all these different kinds of things. And so for me, like, thinking back to my own childhood of the Commodore VIC-20 and early programming and fractals and SimCity and all this kind of stuff, there's all these really exciting areas that touch upon so many different aspects of our lives in this kind of almost like humanistic liberal art sort of thing. And that's essentially the point of the book. The book is designed to rekindle that sense of wonder and understanding, and hopefully provide a healthier way to approach computing, one that kind of connects the human with the machine and can hopefully, at least somewhat, repair a little bit of society's broken relationship with tech.
Reading it from the outside as somebody who wasn't a coder, and I regret in some ways I missed that whole revolution that happened. I remember we had actually Max in the computer building, and we had a very old priest. He didn't even know how to use them, but he was like this guardian of the computers. So it wasn't very welcoming. And actually, you talk about the importance of serendipity as well here. Like, for example, you talk about SimCity and how SimCity inspired plethora of people to go into city planning as a result. And I was thinking about how those important little serendipitous moments can just redirect the course of your life. But reading it, it was really clear to see that this reason you write this, The Magic of Code, is it really is in a way a history of how we got there, but also an ode to code and your celebration of it in many ways. Maybe you'll tell us a little bit more about that.
Right, like, it is this ode, and yeah, it's like this paean to this kind of stuff. Because I mean, and for me, and I think I might maybe mentioned this in the end notes, I can't remember exactly where, but in many ways, this is the book that I wish I had when I was first getting into computers. Like, I had to cobble together a lot of these different ideas on my own. And so this is sort of my own way of like paying it forward to like future young Sams who are beginning to think about these kinds of things. Because, right, there is all of this wonder in these areas, and too often we've forgotten it. And so I don't think I mentioned this story in the book, but so my grandfather, he lived to the age of 99. He was a dentist, but in addition to being a dentist, he was a lifelong fan of science fiction, and he basically read it since like the modern dawn of the genre. I think he read Dune when it was like serialized in a magazine. Like, he knew all the different stories. And so I remember when the iPhone first came out back in, I guess, 2007, something like that. I went with my grandfather as well as my father to the local Apple store to see the iPhones. We're playing with it. And at one point, my grandfather says, he's like, "This is it. This is the object I've been reading about for all these years." And like, it really was something out of science fiction. And yet we moved so quickly from that to, I don't know, complaining about battery life or camera resolution or like weird buggy apps. And like, we've forgotten that. And for me, I think we certainly want to. I don't think you can live with that like sense of like transcendental wonder at every moment of your life, but we shouldn't take some of these kinds of things for granted. And so for me, I think about like, how can we have this sense of wonder in our computing? And I talk about the nature of like enchantment and disenchantment. And so this is by analogy with the way people have talked about how like we went from a world that was full of enchantment of like, I don't know, magic and sorcery and gods and powers and all these different things, to one where that was, in kind of the era of the Enlightenment, no longer the default. And using that kind of framing, I talk about digital enchantment, not necessarily thinking of like this stuff is magical, but more in the sense of it actually elicits the sense of wonder. And there's a simple narrative that you can tell that says, oh, we back in the day when computers were simpler and people were doing all these weird things, there was lots of enchantment. And then things were disenchanted by virtue of enterprise software and just building these things and software teams, stuff like that. The truth is, that's not really the right narrative. In fact, the digital enchantment and kind of like the wondering approach, alongside this more utilitarian kind of enterprise software kind of approach, they've always coexisted. So back in the day when you had really large computers, there were these very large mainframes and they were the province of companies or universities or large labs, and you were very distant from them. But then alongside that, you had like mini computers, well, maybe a little bit later, that were still very large. And they're called mini, but they're actually like the size of a refrigerator. And that was where some of the earliest computer games were developed. So like Space War was developed during this time that was still very corporate. And then once you moved to like personal computers, you both had the advent of like the spreadsheet and computers in offices, but then also personal computers that were geared more towards delight, like the Macintosh and all the early weird shareware and all this kind of stuff that was around then. And then even now on the web, you both have things that are the province of big tech that feel not necessarily that delightful. But then you have an entire realm of what people call the poetic web, which is just the websites that are almost like works of art or fun and delight. And so for me, not only have these things always coexisted, but they often play off of each other. So oftentimes, the more utilitarian frame, they actually provide the foundation for the people who want to build the more wonderful stuff to actually do it more easily. And then conversely, the wandering stance, the really delightful things, the poetic web, whatever it is, that can then actually help get people excited about getting into software more broadly, and then maybe build more of these other kinds of things that maybe are not as delightful, but still very important. And so for me, when I think about wonder, it's not just something that we used to have or that we've forgotten. It's always there, but we need to search for it and find it, and then use it, because it actually is very, very important for kind of moving computing forward. And what is that wonder? What is that the source of wonder in computing? It can be lots of different things. And like going back to like this kind of liberal art of computing, it is, for me, it's building computer programs that are works of art, or thinking about how to actually encapsulate biology in computers, or simulations, or SimCity, or all these different kinds of things. And we can talk about all those, but that was the goal, was to show that this wondering stance not only is very powerful, it's always been around. And in fact, some of the most interesting things around what computers are doing, whether it's AI or weird things with artificial life, they were actually present very nearly at the advent of the modern digital computer, like decades and decades ago. But it took a long time for them to just, I guess, like percolate and become a reality, or at least something that people can use more. So we definitely need more of that sense of wonder in our computers.
That idea you share about shifting baselines, but also I think it was John McCarthy you quote as well, like who's it's not considered AI once it works. Was it
Yes,
that
yeah,
ring a
you're right.
bell?
Like, right, because AI, I mean, certainly, I feel like now it's changed a little bit because some of the things are just so impressive. But you're right, for a long time, the realm of artificial intelligence, it was at that frontier of things that weren't quite able to be done, that kind of mimicked certain features of human behavior. And then once they were solved, you're like, oh, this is actually just some weird trick. It's not really AI, it's just some other branch of computing or whatever it was. And we forget, right, that we have been making very, very powerful advances along the way, even if, yeah, we're not willing to have that sense of wonder or consider it to be truly AI or whatever it is.
I'm gonna mix it up now because there's so much in the book, and I really loved part three and the end of part two as well, where you're a trained biologist as well, which I didn't realize. I knew you were a polymath, but I didn't realize that until this book. And I can see now your curiosity around biology and also genetics and all everything in that realm. But when I read about that, I was like, AI essentially has evolved in a similar way, in a similar fashion, the same way as biology does in DNA, for example. I'm grabbing pieces from the future and bringing them into part one there because they mix well
Yeah, no,
together.
yeah. So in there's two chapters near the end of the book where I discuss various different aspects of biology and the realm of computing. And one of them is just simply to look at the ways in which biology and computation are similar and different. And so, because there's certainly analogies to be made to how computation works, to how biology operates. And so I discuss like two frames of how to think about biology. One, and the first of which is the realm of the information, where you look at the informational aspect of biology. And you can say, oh, by analogy, with computers that have binary zeros and ones, DNA has four base pairs, the A, T, C, and G. And so, like, oh yeah, it's storing information somewhat differently, but it's storing information. Then that information is being processed in a certain way. It goes from DNA to RNA, and then eventually is turned into these proteins, that then act in the system. And so there's this very sort of computational aspect to it, where like machinery is taking information and actually making it do things. And so that's the very nice kind of information view. But of course, there's also the view of the mess, which is biology is wildly different from computers. It is deeply, deeply messy. And so you have like at the organism level, like we're these kind of like weird, wet, squelching messes, very different from computers. But then once you move down to the cellular level, cells, they might compute or do things and manage information, but in a very, very different sort of way. So if you zoom down to a cell, it's not just, oh, here's some information, it's being taken to this thing, moving in like a very nice kind of flow chart. It's a whole bunch of molecules just jittering around and moving in this massive mess. And sometimes regularities emerge from that mess, but it really it's highly parallel, it's very random and stochastic. It's a qualitatively different sort of thing. And for me, one of the and that being said, you can still map on certain kinds of things to the world of computing. But for me, one of the most interesting things is recognizing that biology, it might still be doing something similar to what computers are doing in some very broad way, in the case of like information processing. But it's wildly different. But it actually what it then shows is that information processing or computation is this much larger thing, and biology is one example that's doing it in a very, very different sort of way than we might traditionally think of computing. And then you also have what happens on our laptops and happens on our computers. That's another thing, which means though that the space of computation is actually much larger than people might realize. And so there's an entire space of what's called unconventional computing, using different sorts of substrates, not the kind of traditional transistors and things like that, to actually compute, to maybe optimize some sort of problem by using, I don't know, a slime mold on on a surface, or DNA to help like factor large numbers. There's all these wild things. And so for me, biology can help us expand our notion of what computation is. Similarly, and then kind of the second chapter where I talk about biology is this idea of artificial life, where you can actually take biology, kind of like strip it down to its bones, and say, okay, what are the features necessary for biological complexity, and can we actually embody them in computers, and then from there actually result in almost like a digital kind of life, but then also learn about biology itself, like find out what are the actual true feature, like the necessary features of of biology. And so this field, this kind of artificial life, which is often the description of it is like life as it could be. It had its heyday, I guess, back in the day, like the 80s and maybe the 90s. It went through a period where not many people were actually doing it. Although my sense is one of the areas where it was still actually being done was in Japan. So Japan tended the fire while other parts of the world of artificial life were not really working on this as much. And now we've actually, in the past couple of years, we've actually seen a pretty exciting resurgence of this field. But one of the examples is like evolution. Evolution is the fundamental feature of life. And it turns out you can actually embody evolution and like the process of natural selection in a computer, because in many ways, natural selection and evolution, it's an algorithm. It's you have a population, there's variation, and then they're being selected for, and then you have a next generation. You can do this kind of thing. And of course, I mean, there's many details that I'm skipping over, and the details really matter. But the fact that you can actually embody evolution in a computer, this kind of like evolutionary computation, is unbelievable, and actually has taught us a lot about how to think about evolution itself.
I love that. And this is where I was getting to, was the idea of the Red Queen hypothesis, for example. But there's loads in there. And I'd love you to give us a little whirlwind tour of these, which was, for example, in the 1940s, there was an Italian researcher who created a DNA sequence. Well, it was a computational sequence, but it was essentially where they competed for resources. And then what was remarkable was that parasites would be formed, which that was mind blowing. And then this was repeated again a few decades later with the Game of Life. I'd love you to tell us about those, because these are just mind blowing when you realize this.
Yeah. So and going back to this idea that inherent in the history of computing are often these ideas that they may take a long time to germinate, but a lot of these fundamental ideas of connecting computing to biology, connecting it to certain aspects of simulation or artificial intelligence, like these things were all inherent very early on in the realm of the computer. And so there was this one man, Niels Baricelli, who he worked with the Institute for Advanced Studies. So John von Neumann, who is a polymath and amazing, I think considered to be like one of the smartest humans who ever lived, he was involved in one of the first digital computers that was developed at the Institute for Advanced Study. In fact, the architecture for all, I would say all, but many modern computers derives from that architecture, which we actually call the von Neumann architecture. And one of the first things that was done with this computer that was developed, I guess, in like the late 1940s, early 1950s, in addition to large scale simulation, were these artificial life experiments. And so this researcher, he had these strings and they all competed, and we're doing these kinds of things. I don't know if the parasite thing was in there, and that might have actually been in a later one called Tierra, where
That's
so
right, Tierra.
there was a later experiment or program, I think maybe in the 1980s, I can't recall exactly, where that kind of, it took some of these ideas, although I'm not necessarily sure he actually took those ideas consciously or deliberately, because a lot of that work from like the 1940s was forgotten for a very long time, and then it was only sort of, I don't know, reinvented or not quite rediscovered, but repopularized more recently. But the program Tierra is this really interesting thing where basically the idea is you have, rather than having like various different organisms or formulas that are competing, and you actually see which ones are the most fit, the actual organism is itself a computer program. There's very tiny little simple computer programs that were competing for computational resources, if I recall correctly. And one of the things that they found is like when you run this for long enough, and actually fairly quickly, I think, you would get parasites. You would get snippets of code that cannot reproduce themselves, but are able to reproduce due to the fact that they're working with like self-contained digital organisms, like their own programs. And And people have actually been building lots of other kinds of programs as well to try to understand these, like the nation or the nature of evolution within computation. But another realm, and you mentioned John Horton Conway's Game of Life, is this idea of cellular automata. So cellular automata are these very, very, and actually going back to John von Neumann, he was actually one of the people who helped develop the idea of cellular automata as well. So there's these very deep histories. But so cellular automata are, imagine you have a grid, and the grid has lots of squares, and the squares can have a number of different states. And so the simplest would be, we can use the Game of Life as kind of example. Simple is, imagine each square can be either on or off, black or white, 0 or 1. And each generation, each time step, the way in which you decide whether or not these dots, the squares, switch on and off is you look to the neighbors. And so, and the way the rules are is that if it's on, if a cell is alive, that, like, if it's a black square, it looks around, and if it's like, I think it's not overcrowded, so there's not too many neighbors and there's not too few neighbors, so it's not dying of loneliness, it continues to persist. And if it has, and I think if a white square that, so it's not alive, has exactly like 3 neighbors, then it is born and comes alive. And then there's it's a high level way of describing it. And so it sounds very simple. You would assume, okay, you get maybe some like little blinking things and nothing particularly exciting. But it turns out, using these very, very simple rules, this example of cellular automata, Game of Life, gives you this unbelievably rich behavior. So you have these things called gliders, which are like a set of like little squares that they all move together and they waggle across diagonally across the screen. You have a glider gun, which actually generates an infinite amount of gliders. People have actually made entire computers inside Game of Life, so it actually is effectively equivalent to modern programming languages. There's a huge amount of variety. And so this was developed by this mathematician, John Horton Conway, I think around 1970. And then soon after, Martin Gardner, the science and mathematics journalist, he wrote about it in a column in Scientific American. And at the time, I think after this column was published, it was so popular and so many people basically just stopped whatever they were doing and tried to find a computer to use to actually embody this in code, that I think he estimated that, like, I don't know, like millions of dollars of computer resources were dedicated to the Game of Life, which is wild. Also, when you think back to like 1970, there weren't personal computers. These were all like large computers that were at universities or companies or things, and so people were actually using all these resources for that. And of course, since then, people have been continuing to develop more sophisticated cellular automata. So there's another one that kind of uses a smoother version of this. So instead of the discrete time steps and like the squares of on and off, you smooth it out to make it more like the real world. And so this version is called Lenia. And it turns out there is a whole like bestiary of organisms that are persistent in these digital worlds. And it turns out you can actually embody this, all of Lenia, I think in like 10 lines of code, which is insane. And so, yeah, it's to see all the different ways that you can take various aspects of biology, whether or not it's the sheer open-endedness of biology, which is still an open question of whether or not we can do that fully within computation, certain aspects of evolution, certain aspects of persistence and resilience and robustness. All these things can actually be tested and embodied within computers.
It's incredible when you think of it that way. And that's why I know you bring people on a journey in this book. And for me, it was quite a privilege to have read the other books, because I'd seen where you were coming from in that early part of the book. But for this book, it was necessary to get people to part 3 to bring them on that journey. But there was a couple of things I just wanted to pull out. One was where this all appears is in the chapter Ghosts in the Machine. And there's a movie about that, and it's an anime. It was an anime Japanese story, which is great. I think Scarlett Johansson is the main protagonist. But the idea of there will be emergent behavior in computation. Therefore, if you have artificial intelligence, there will be emergent behavior as well. And I thought it was interesting. There was a little line I just pulled out, and I just would love you to elaborate on this when you said, all around us are clues that if the tape of life on Earth were rerun, it would look very different. And I was like, that's an intriguing line. Let's elaborate on that one.
Yeah. And so, evolution ultimately is entirely contingent. And so it is not a given that if intelligence arises, that intelligence will come in the form of Homo sapiens, of looking exactly like humans. There's many, many different ways that evolution can solve problems, and can solve problems of adapting to different types of environment. And this is because, like, evolution by natural selection operates by dealing with variation and exploiting random mutation and things like that to then create organisms that are fit to their environment. And of course, there's coevolution, all these other kinds of things. But if you look around, I mean, there are no dinosaurs anymore, but like, were dinosaurs not particularly fit for their environment? They were actually very fit for their environment until there was a massive cataclysm that kind of destroyed their environment. And so it, like, the fact that mammals are now, and intelligent mammals are the dominant form of life on the planet, is not a given. And if you look at the historical record, like the fossil record, you see all these weird evolutionary dead ends. Sometimes they were dead ends because maybe they were not fit. Other times, though, it's because of some sort of environmental disaster or whatever it is. And so you can see all the different paths that evolution could have taken. And you see this. And sometimes you can even see it in terms of even just you can see a little bit of that evolutionary history or the history of the world in some of the things that have not adopted yet. And so we talked about when we were discussing our conversation with, like, Overcomplicated, about like the honey locust tree that still has the giant spikes to protect against the megafauna of North America that don't actually exist. And so there's just all, but then you also have things about, like, when you have these environmental disasters, you can end up with a very small, non-random subset of a population that then actually becomes the population for the future. So this is called like a population bottleneck, where there's like some situation that causes a very small population to move forward and then repopulate some area. And of course, if the small number have some weird genetic trait or whatever it is, then that is going to be the thing that is quite common in the resulting population, even though it's not necessarily something that's fit. It just, that's where it is. And so I believe there's some island that I think has a very large amount of color blindness.
Pinglap.
Yeah,
Pinglap
and
Island.
I think the thinking is like, yeah, there was just some sort of population bottleneck. There was some sort of disaster, and you can see, right, like there were like certain populations might have relatively high rates of certain genetic diseases, and in certain situations it could be because a small population that had that relatively high rate populated that new area, and so that kind of led to certain things. And so there's always a certain amount of weird contingency, and as a result, when you run these evolutionary computation algorithms, you're not always going to get the exact same result, especially if it's like some really complex problem that you're trying to solve or some complex thing you're trying to do. There might be many, many different ways of solving that kind of thing equivalently.
I always think about that, for example, with the great controversy of vaccination. Do you get vaccinated? Do you not? And you're going, well, that certainly plays it out differently for different populations who did or didn't get vaccinated, etc. We have no idea how that would that will play out in the future. And then I'm not going to go there, but then there's the whole quantum field. Is they're all happening? All those different choices happened at the same time. Mind blowing stuff. But speaking of which, we now get to the true endpoint of all this talk about reality, physics, and computing smashing together, as you say in the book. And just as we can focus on the realness of computing, its profound physicality, what if we can posit that reality itself is a program found within a computer as some kind of grand simulation? So, this is the core message you get to. Well, not really the core message you get to, but what you build towards in part 3, which is the simulation hypothesis. And I thought we'd get there rather quickly because this is something that people really find it hard to get their head around. But actually, reading your book was the easiest way I've got there. And maybe we'll even rewind a little bit, Samuel, and go to stuff like Sims and games you grew up with and played quite proficiently. I mentioned, for example, SimCity earlier on, but how they work. And then actually, well, if computing power is so powerful, how would they work going forward?
Yeah, I mean, so yeah, taking a step back and like thinking about like simulation in computers, right? Simulation has also been one of these features of digital computers since the very early days of computing. That was like often one of the things they were doing was like trying to, I don't know, understand trajectories or nuclear simulations, things like that. And the question becomes, right, how can we embody all the details and complexity of reality within a machine and understand it in some sort of reasonable and meaningful way. Because there's always going to be a distinction between like the map and the territory. Like the model you make is always going to be some sort of simplification. Sometimes a like necessary simplification because you actually want to abstract away details in order to understand some specific thing. Sometimes it's also just because we don't have the like a huge amount of data or the necessary amount of data. We might not necessarily understand all of the forces that are relevant for the features of the world we're trying to understand. That being said, and they're also just fundamental constraints of like certain things around like chaos, chaos theory or whatever, where like you run these things and it's very hard to actually predict things beyond a certain time horizon. That being said, like if you look at like weather, for example, we've actually gotten much better through the combination of like much better data, better algorithms where you can combine different models together, as well as just massive advances in computational power. And slowly but surely, we have gotten better and better at understanding the nature of the weather and actually being able to predict it. Now, of course, prediction is not the only reason we actually simulate and we make models. And I alluded to that before when I said like you can sometimes make simplified models where you just want to understand some specific feature. Or with SimCity, and SimCity certainly had an impact on a lot of people who ended up going into city planning. But it was a necessarily simplified version of the world, and probably so simplified that it was like wildly inaccurate. That being said, it was a lot of fun, and it also gave certainly me, and I imagine many other people, a deep understanding of the massively nonlinear nature of the world. Where like if you are truly trying to understand a complex system, you need to see how things have second order effects, unanticipated consequences, how decisions bite back, how the system bites back, all these different kinds of things. And you got to experience it in SimCity, even though it was not making any claim that it was the real world. Now the question becomes, right, like if we make these simulations more and more sophisticated, what could the potential endpoint be? And you also mentioned kind of like the physicality of computing. I'll just kind of take a step back and mention that with like we think of code as this like ephemeral like thought stuff. And in many cases it's useful to think of it that way, but computation ultimately is deeply physical. And like we're running things on actual computers. We have data centers that require huge amounts of energy, and you can see like the deeply physical nature of computing even like in weird glitches and failures. So there was this story I read, I think it happened a couple of years ago, where it was in some hospital and people noticed that their iPhones and their Apple Watches stopped working around some MRI machine. But Android devices were actually fine. And it turned out it was that this MRI device had a helium leak, and it turns out the helium atoms were just the right size to like interrupt the switches in Apple devices, but not Android devices. And so we often like forget about the deeply physical nature of computers at our peril. And so when you think about what are the endpoints of, okay, huge amounts of computational resources alongside kind of the endpoints of computation, like how much computation you can actually make in like, I don't know, a kilogram or whatever it is, you end up doing these very weird thought experiments of thinking about, okay, what are the true endpoint of computational resources? And then that leads into what can you actually simulate? What can you model? And could it be then that we are maybe inside a simulation? So like this is the idea of the simulation hypothesis, that like everything we see around us, like you, me, ourselves, the entire world, we are all inside like a version of SimCity and just don't realize it. And so, and for me, to be honest, I'm much less concerned with like whether or not this is true. Like I don't view it as like this question of like great cosmic importance. I feel like that's more kind of like like the kinds of discussion that is better for like undergraduates late at night talking about, versus for me, when I think about the simulation hypothesis, it often feels like this kind of cry for mythos or like a great deal of meaning. And so like, you look at like societies, like we always have a need for mythological tales or large overarching theories to understand the world. And you see this even in certain kind of like theories within the realm of science and technology, of like people talking about like singularity or superintelligence or like Fermi's paradox and aliens. And then also the simulation hypothesis. I feel like it like slots into that place where people are trying to find some bigger thing. For me, I don't necessarily, I don't really find that compelling as like, oh, like it's like this big thing. I view the simulation hypothesis as provocative in the sense of, if we are in a computer program, let's think about what it would mean to be inside a computer program and, I don't know, inject unexpected bits of code. And so then that kind of leads you more towards, less towards the realm of like cosmic importance and more towards thinking about glitches and failures and like code injection and weird just like exceptions and things in the realm of computation. So for example, there is so Super Mario World, which I think it was for the Super Nintendo like decades ago. A group of people figured out that if you move around in this game in a certain specific way and like jump in specific locations and at certain timing, you can actually reprogram the game itself. And then eventually you can like, and so I watched this video where someone did this in such a way and then turned Super Mario into a version of Flappy Bird, like an entirely different game. And which is not to say that like if I just jump around in my office a certain way, I'm going to reprogram reality. But these are fun thought experiments to think about. And so and it can also lead you to think about going back to like the deep physicality of computing. Like what are the endpoints or the limits of simulation, the limits of like physical computing? What would that actually mean? People have actually tried to calculate this and explore these kinds of things. And so for me, those are the kind of things that the simulation hypothesis makes me find much more interesting. So for me, it's like not like, oh, like this is the thing I need to think about and worry about. It's more, simulation hypothesis is a wonderful provocation to get me to think about more really big questions about computation itself.
I have a similar kind of approach to it. Like, it's interesting, and all those theories are interesting, but it's more, what do they mean to you with your beliefs and your belief system as well? And also, how do they help you? Like, for example, injecting the code could be, well, I can actually have a certain amount of control over my reality. If I if I behave a certain way, then the universe behaves back to me in a certain way, and it creates this feedback loop that actually can lead me on different pathways and stuff like that. So they're the kind of things it forces me to think about as well. But there's a great saying that it's hard to read the label when you're inside the jar. And actually, it's perfect for the simulation hypothesis. Well, how would you know? And
Right. Like in the absence of like very clear evidence, right? It's just a fun speculation. And so for me, it's like where can that fun speculation lead in insightful ways about how we think about computing and reality. That being said, there was a great novel that came out, I think sometime in the past year. It's called When We Were Real. And the premise is like, I don't know, 7-8 years before the story starts, the world is revealed to be a simulation. And then in the story itself, it is a group of people going on a bus tour across the United States to visit all of the locations that are like basically glitches in reality, that are these like roadside attractions that provide evidence of the simulation hypothesis. And it is wild and fascinating. And you also just see, and he explores like how people would respond to these kinds of things and think about it. And yeah, I highly recommend that book. It's fantastic.
it sounds like going to the certain places in Super Mario World, jumping over there in the corner. And actually, just to mention Carl Sagan, who noted, and you say this in the book, we have become a mechanism for the universe to study itself, understanding physics and biology and even computation itself. I love that little quote, which brings us to the wisdom of computation, the final chapter. And that chapter, I felt, was less about machines, and it's a shift towards mindset again. And again, while it's clear you're a lover of code and the history of code, and probably one of the most researched people I've ever read on this, I left a review on Amazon and I said this. I was like, imagine a polymath who was fascinated by code and language and a plethora of different subjects, driven by curiosity, writes a book. Well, that's what this book is.
Thank you for the kind
And
word.
and I just wanted to touch on this. I mentioned language, actually. Let's go there quickly, because I thought this was a really interesting point you made. You said that language is really how we think, and language, that Wittgenstein quote, "The limits of my language is the limits of my mind," or something like that. But also, I thought this was fascinating that you said our LLMs can be biased because of our language, because at the bottom, we train an LLM on text and it learns from our stories. A narrative is based on what yields a good yarn, one that slices away extraneous or complicating detail. There is always a distinction between the map and the territory. Since these models are ultimately built upon language, we might forever be stuck in the world of stories, simplifying narratives, and tales that lack loose ends or confusing details. I thought that was a really interesting insight that we might share.
No, thank you. Yeah. Yeah, right. Language, right, especially with these large language models that we're building, they are built on these like mountains of text. Now it's changing a little bit more as we have like multimodal ones which are using images, and maybe when we're beginning to train systems for robotics, they're actually going to engage in the real world. But the large language models, they are trained on the vast amount of text that we have generated as a society and as a species. And text, right, like the text in the world and our stories, right, that is not reality. It is necessarily simplified. And we forget this at our peril, that the way these systems work is they are trying to map things on to, and sometimes like literary tropes, other kinds of things, or like certain, like in the same way you see like certain chatbots will have like certain personalities or personas that they will take on because that's the thing that you see in text. And so there, a number of people have actually talked about this as, I think they describe it as like semiotic physics, where there's a physics in the system, but it's not necessarily the physics of reality. It's the physics of language and text. And so one of the examples someone did was like having these systems like generate random numbers. And it turns out these random numbers are not actually statistically and mathematically random. They're things that maybe feel random for humans. And I actually I recently did this with Claude, where I said, okay, generate like 100 numbers, like 100 random numbers, like between 1 and 10. And so it gave me this whole string of numbers. And then I said, okay, now make a histogram. And as soon as it made the histogram, it responded, oh, these numbers are not random at all. Because it was like the exact same number. And then I said, okay, then we had a little conversation about like about this. And I said, okay, now that you know this, now do it again. And I did it again. And it was like a little bit better, but it still recognized it was not anywhere near random. It's because, right, like these systems, they are trained not on reality. And you can sometimes sidestep it by having it actually write code to do pseudo, like actual like math, like computational pseudo randomness, as opposed to the weird things that feel random to humans that are not actually random at all. But yeah, we're stuck in this kind of thing where it's almost like the situation where if you know these narrative tropes, you will better, and like in the way stories are written or constructed, you will better understand how these systems make meaning. And actually, the novelist Robin Sloan, his most recent novel, Moonbound, actually discusses this kind of thing of like these systems have huge amounts of information, but they are ultimately bound by the realm of text and the kinds of text that we generate as a society, and that causes these kinds of things to be biased away from reality and towards certain aspects of language. And so that's one of those things where we just have to be very aware, and returning to humility. Like we have to have humility about the powers of these kinds of systems.
It's why I write a weekly article. I've included you in many of them, and actually in a few forthcoming as well. But I'd never use AI to come up with my ideas. I'd feel like such a. I'm not saying you are. If you do, if somebody's out there using it, but I would feel like I'm a fake in some way, and also that I'm not adding any value because I haven't drawn from my own reservoir of thinking and ideas that marinate. And it really leads me to this point that AI can help you maybe structure it. And even when it does that, I don't like what it does because it writes in a way that is too, I don't know, it feels too sterile for me. It's not human and broken enough when it produces something. But I don't feel I'm adding any value that's different and something that's truly human and draws from very disparate fields, much like your writing as well, where you're drawing from different places. I like to write in analogy and metaphor, and I often find that by doing the show and reading in these different areas eclectically, you can come up with great ideas that are just different. And then you train it. And you have a beautiful line where you say that AI or code is a model for thinking, not a replacement for it. I think that's a really important aspect that we need to get across.
Yeah, no, I completely agree that like ultimately, right, these systems should not be replacing the things we want to do. They should be augmenting. There should be the kind of this human machine partnership. And so, right, there's this whole realm of computational tools for thought. Like these tools that kind of help us to make connections or store notes or better understand models of the world. And these are very, very powerful. And AI is certainly one of these kinds of things. And that being said, though, like as AI is getting more and more powerful, it can cause worry of like, oh my God, like, can it do all the different things that humans can do? And so for me, I think about this kind of by analogy with an idea from theology called like the God of the gaps. And the idea behind this is you have like what is like in this case, like how would you define God? Oh, God is anything that science has not explained yet. Now, of course, that there's a fallacy there because as we develop more in like astronomy and cosmology and evolution, suddenly that conception of God gets smaller and smaller and evaporates. And I feel like we're doing the same kind of thing when we think about AI, where we say, oh, like this AI system is impressive, but it can't do the following things that humans can do, like X and Y. And of course, you wait like 10 minutes and then suddenly AI can do those kinds of things as well. And so for me, it's less about saying, okay, what is essential to our humanity of like, oh, we're tool users, which then I know we've discovered not aliens, but we discovered animals can do these kinds of things, or capacity for language. And the same kind of thing we're seeing in AI of like, oh, AI can't do this, but now it can. We need to focus less on like what is unique about humans and what is quintessential to our humanity. And that is something that each of us need to figure out. Like what is quintessential to each of our humanity is like the things that we truly want to do. It can be thinking really well. It can be spending time with our children. It can be gardening. It can be doing hobbies, things like that. You wouldn't want a system to do those things for you even if they could do them, because these things are quintessential to your own humanity. And so you have to find ways of using these tools to make sure you make yourself the best version of that. And so this kind of goes back related to the tools for thought idea of a phrase from Steve Jobs called like, a computer is a bicycle for the mind. And so this idea is that it was based on, he read an article in Scientific American where there was this chart looking at like the energy efficiency of different organisms. And you had like, I don't know, certain like birds were maybe more efficient or maybe less efficient. I don't remember exactly what it was. And like humans were okay, but they also include a human on a bicycle. And suddenly everything changed. Humans are much, much more efficient when it came to actually moving like mobility on a bicycle. And Jobs' idea was like computers are the same kind of thing, but for the mind. Like they're a bicycle for the mind. And we have to make sure that we constantly have that in hand when we're thinking about these technologies. They should augment us and make us more efficient and better versions of ourselves, but they shouldn't necessarily guide our decisions entirely or remove the actual things that we want to be doing. And so they should be like there should be this kind of human machine symbiosis or partnership or whatever, this kind of productive relationship that allows us to actually retain what we view as our quintessential humanity.
Which brings us back to the Red Queen hypothesis. When I thought about that, I thought again about the idea that we're seeing a bit of a Red Queen race, an arms race with AI, and most of it's in pursuit of power. Or, for example, I don't want to be the country left out here, so I'm going to do it quicker. And oh no, well let's cease let's cease the race for the moment, and then you go, don't cease the race, keep going. And that's a whole challenge that we're at the point in history as well, because we are opening up Pandora's box. And I'd love your thoughts on that.
Yeah, I mean, it's one of these situations where, right, as we are developing more and more complex systems and complex technologies, more advanced technologies that require huge amounts of resources, right, to unilaterally disarm feels like, right, like just basically like admitting defeat. And so, how do you do that kind of thing? And like, how do you retain your humanity or kind of feel as if like you're choosing to adopt certain things as opposed to just this like wave of technological advancement kind of washing over us? I do think, I mean, it's hard, but I do think we still do retain a certain amount of agency and control and like choice in which of the things we choose to adopt. It is very tough sometimes, but I wonder if like there will be the ability to actually build things that are more at a human scale where we can make things more in line with our humanity as opposed to just having big tech forced upon us. And so and that kind of like that small human scale, I think that is probably the key of like how do you make things in line with our humanity and what we actually want? You probably have to make software and technology that feels not so big and not so not so much of an imposition upon us where we are not we are not bending ourselves to our technologies. We are, in fact, using technologies to make us the best versions of ourselves. And for me, I see hopes in that, I guess maybe surprisingly, by using some of these AI systems, which is around the idea of like democratizing the creation of software. So for a very long time, I mean, software has been like you have to be really, really like well trained to you have to. It takes a lot of effort to actually make software, but there's been a dream for many years of actually allowing a certain democratization of this, where each and every person can build the software that they want for whatever needs they want. And so, actually, to return to the novelist Robin Sloan, he has this wonderful essay where he talks about an app as a home cooked meal. Where, like, in the same way that, like, when I'm cooking, I'm not cooking for like thousands or millions of people. I'm cooking for me or my family. Like, you can do the same kind of thing with software. Like, you should be able to build things just for yourself at that kind of smaller scale. And intriguingly, AI, especially with like the advent of vibe coding and code generation, it really is allowing us to do those kinds of things. Now, to build much more sophisticated software that would require like like it being secure and maintaining privacy, so like you need to really know how to actually like build software. Like you need to actually know how to code. You can't just take the thing as given. It could be not so great. But for building something for yourself or for your loved ones or whatever, that's great. And so I actually think this democratization of software creation might actually allow us to more easily build a world of technology that is more in line with our own needs and desires and wants and on that human scale.
And to go back to something we talked about before, the limits of human consciousness or limits of our cognitive abilities are overrun then, for example. So, one of the things, you're a polymath, that's clear from reading your work, that all these different realms that you've drawn on, that actually that's not something many people can do. And as we talked about in the last episode, we need more people with that type of range, or that type of breadth of knowledge, because there's often solutions for your challenge in a totally different realm over here, and nobody's connected the dots. And that's one of my hopes that AI can do, is if it is fed these different realms, that you can actually solve big problems in different realms, different arenas that have been hitherto unseeable for many people as well. But I mentioned the mindset piece, and I thought this was so important, that you talk about the importance of humility, restraint, and curiosity comes up time and time again. But alongside this humility, you say we must think about code as something that must be developed in line with our humanity, rather than as something that tries to subvert its nature. To reiterate what was explored in the chapter on tools for thought, we must avoid bending ourselves to the needs and whims of our machines. Computation should not narrow our humanity. The real world is messy and wonderful, and we must be deliberate in how we balance all of this. I absolutely love how you wrote that there as well.
Oh, thank you so much. I really appreciate that. Yeah, no, I think right, like that is really the goal. And I feel like sometimes when we get so obsessed with technological advance for its own sake, or kind of just like things that seem amazing and powerful, like we forget like really what is ultimately the goal. And so there was a TV show that came out probably like a decade ago or so called Halt and Catch Fire, and it was about the early computing industry. I think it went from like 1980 to like the mid 90s or so. But early on in the show, possibly even in the first episode, someone talks about computers and they say computers aren't the thing. They're the thing that gets us to the thing. And it's all like too often we just constantly want to advance our technologies for their own sake without realizing no, there is an end point there, which is like making us better versions of ourselves, making us in line with our humanity, allowing us to help us connect different ideas, acting as tools for thought, making us better able to just live in the world. Like these are all the things that we should be focusing on. And so I think as long as we have that in mind of recognizing that these are ultimately tools, and we have to choose how we actually use them in a way that makes us the best versions of ourselves and in line with our humanity, then I think we'll hopefully be in good shape.
I have a final quote that I loved, and this is where you were talking about your daughter who is intrigued by watching you drive and looking at places and how you react to the traffic lights, preparing for her future of driving, and you're like, let's not talk about that, yeah, because it might not happen because of autonomous vehicles. But here, there was a little quote that I'd love to share as my finale. As I'm doing that, I love you to think about your final message. But you wrote here beautifully: change happens, but we live among the remnants. Ruins is probably too strong a term of these forgotten technologies. Cars have CD players for compact discs. Few people buy these days. Libraries allow you to borrow DVDs even if you stream all your movies and don't own a DVD player. You view these less as the inertial burden of technology and more as layered mementos of people's predictions of the future. They are reminders of our inability to recognize that the future will be different from what has come before. Technological change is not a simple extrapolation of what we have now, only a bit faster or sleeker. It will be qualitatively different. Now, I share that for many reasons. I love what you wrote there, but also I always think about the poem of Osmandias, and the great king that has this statue to himself and it's blowing in the wind, and that everything we do in life, we can fall into the trap of thinking it's so important and forget that you got to live and you have your family and friends and all that kind of stuff. And people fall in love with their job or don't, or just falls in love with the dopamine hit and the stress of doing that job over and over. And these kind of little quotes here remind me of that it's not really that important. And it's hard to read the label when you're inside the jar. And sometimes those kind of quotes where you read all those people who built all those technologies gave up so much to do so. And then I go back to what you talked about earlier on about the idea of asymptotically creating new technologies. So you talked about the guy in the 1940s the Italian gentleman who created the code sequences, probably wasn't even remembered, but that technology was built upon then later, decades later, with the Terra, what was it
Tierra,
called again?
Tierra, yeah.
The Tierra game, or the Tierra sequence, and surely that will be built upon in the future. And people forget about all those people who have built a little bit towards where we're going in the future. But it was so important for those people in the moment. And I just loved what you wrote there as a reminder of that, and that don't take it too seriously. Be serious about it, but don't take it too seriously because life is more important. But I'd love you to close our finale of the series. I've absolutely loved talking to you. I've learned loads, taken buttloads of notes as I've shared with you as well. But what's your final message and why you do the work that you do?
Yeah, no, thank you so much. I mean, yeah, final message. I mean, and ultimately the way I explore the world, right? And right, there is a great deal that is not known. We don't necessarily know where these technologies are going to lead or how scientific advances are going to change and grow over time. And so for me, certainly studying technological history is incredibly valuable. Understanding how ideas have changed over time is also vital for understanding these kinds of things. But I would say ultimately I'm driven by these two ideas of humility and curiosity. Like humility in the face of, right, our technologies are constantly changing. It's very hard to predict what is next. Like the sense that our work, right, we might think it is of like great importance now, but it will be forgotten and like laid bare by the sands of time in a short amount of time. So having humility on so many different dimensions, I think is vital, but also it's a really good counterbalance towards so many of the forces that we see in society right now. But I also think it needs to be balanced with curiosity and like this kind of like omnivorous curiosity, because as the world becomes more and more complex and we build giant technologies that draw from many different areas, or discoveries or advances are connecting different things, being curious about everything and then seeing ways of connecting these ideas together feels, going back to our discussion of our humanity, like a very deeply human thing that we need to do. And it also just, it provides a sense of context, a sense of wonder. And so that like constant drive, these constant drives of like keeping humility in every aspect of what we're doing, of how we think about what we know, what we understand, what we can build, what will have meaning, what will have lasting significance, alongside just this constant omnivorous curiosity. Those are the things that drive me. And yeah, hopefully I was able to convey a little bit of those in the books that I wrote.
The common thread throughout, and it was an absolute pleasure. Author of The Half-Life of Facts, Overcomplicated, on the shelves there behind me, and his latest book, The Magic of Code, Samuel Arbesman. Thank you for joining us.
Thank you. This was amazing.
And thank you as always to our sponsor, Kyndryl. With a unique blend of AI-powered consulting built on unmatched managed service capability, Kyndryl helps leaders harness the power of technology for smarter decisions, faster innovation, and a lasting competitive edge. You can find Kyndryl at kyndryl.com.